Hello. In the previous video, we studied this method, and in the video before the previous one, we studied how to use integrals to find area of a region enclosed by graphs of two functions. Okay, so today we study the washer method, which is an analog of the problem how to find area of region enclosed by two curves. Okay, so let's remind us about the this method and formulas in the this method. It really depends on how we rotate our object, right? So if you have horizontal axis of revolution, then the formula of the volume is v equal to pi integral from a to b rx square dx. Okay, so we have rx in here, and the picture looks like you have this. This is about the x-axis, right? This is the x-axis, and then each time you need to make a cut. That cut should be perpendicular to the axis of revolution. You see, perpendicular, and this is what you have rx. Okay, so we can find the volume using this formula. Okay, so this is just delta x. If the axis of revolution is vertical, so you have the following one: vertical axis so if the axis of revolution is vertical, so you have the following formula: volume is equal to pi integral from a to b from c to d. Let's say that, let's change that, and here you have ry square and then dy. Okay, so the picture looks like this. You rotate about the y-axis, you have this, and then since the axis of revolution is vertical, so you need to make a cut which is perpendicular to this, right? And of course that is ry. You express x as a function of y. Okay, so you apply the first formula for the x function, so you have this formula, okay, where you have c is here and then d is here. In this case, a in here and b is in here. Okay, so you see it really depends on the revolution, and of course sometimes you might express x as a function of y, so everything is good. All right, now if you have two functions, right, you have two functions like this. So you can see in this picture you have two functions. The first one is this one, the second one is this one, and you have a hole, right? You have a hole, and you want to rotate this part about the x-axis or about the y-axis, and you need to find the volume. So on this picture you will see with respect to the first curve, right, you have one solid region, and you can find the volume of that using the formula right here. Okay, it will rotate about the x-axis. And with respect to another one, so you have this curve. Again, you might find the volume of a solid region obtained by revolving that curve about the x-axis. And the volume of the solid region obtained by revolving this part, right, about the x-axis would be the difference. So I need to take the difference. Is it correct? I need to subtract them, like like the problem of area enclosed by of the region enclosed by two curves. So you need to find the area of the bigger region, and you find the area of the smaller region, and then you take the difference, you get what you need. Okay, so I may have the following formula: if you have one function, which is, I write in here rx square, I have pi in here, integral from a to b dx. You have another one, ab, with a smaller one, rx. R small means, that is the function which is smaller than, r capital, okay, dx. Then, the volume should look like this. And sometimes you can compare, you write rx square minus r small x square in here and dx. Is that correct? So if you compare this formula with the formula in here, so the area is equal to integral from a to b f of x minus g of x. Okay, so you would think, yeah, that is very simple analog. Okay, so let's consider the following example and we'll see how that works. You have function y equal to square root of x. Another function is y equal to x squared. Okay, they ask us to find the volume of the solid formed by revolving the region bounded by the graphs of these two functions okay, and about the x-axis. It's similar if you rotate about the y-axis, but again we need to solve, right? We need to express x as functions of y. All right, so right now we don't know which function is bigger, right? And we don't know how many intersections. You remember that? When we solve such problem, right? We need to find the number of intersections, because sometimes we are in this situation. You see, sometimes we have three intersections, so we have two regions, and it really depends on the number of intersections. We need to break the integrals, right, into different integrals. So that is the first step we need to do. Find the intersection between these two guys, okay, between two graphs. So let's do this. I don't know the graph, but let's find the intersection. So I put square root of x equal to x squared. From here, I might square both sides. I get x equal to x to the 4, right? And then I have x to the 4 minus x equal to 0. So I factor x out. I have x cubed minus 1 equal to 0. And then from here, I get x equal to 0 or x cubed equal to 1, right? So you have x equal to 0 or x equal to 1. The graphs intersect at 2 points. So you might think, yeah, you have something like that and something like that. I don't know which graph is above another one, right? But we know exactly. You have, two intersections, 0 and 1 in here. Okay? And 0 is the origin, so we are here. So we need to rotate, right, this region about the x-axis. Is that correct? Now we just need to apply the formula, right? I'll tell you this, right? Even we don't need to know which function is bigger. I just take the difference and evaluate the integral. If the integral is negative, so the volume would be absolute of that value. Does that make sense? So I can write like this. The volume is equal, or sometimes it is acceptable to write plus minus, okay? Means, if the integral is negative, so you take negative, but if the integral is positive, so you just keep the positive. Integral from 0 to 1, the function is x squared minus square root of x dx. Okay? Oh no, sorry. We need to apply the square, right? The square in here. Square. So that should be x squared and then square minus square root of x and then square. Then you have that is plus minus pi into from 0 to 1 x to the 4 minus x dx. Then you have plus minus pi, antiderivative of x to the 4 is x to the 5th over 5, and then minus x squared over 2, evaluated from 0 to 1. At 0, the function is 0, right? So we just need to find, value at 1. So I have 1 over 5 minus 1/2. So you can see actually that is pi plus minus in here and 2 minus 5 over 10. So, this is negative 3 over 10, right? So I just pick negative in here. So I get 3 pi over 10. Okay? Again, right? Sometimes we accept such things because we don't know. We don't know about, the value, the sign of this integral. We don't know it is positive or negative. But if that is negative, means, the function x squared is less than square root of x on the interval, right? On 0 and 1. We can prove that easily, but, since we have only two intersections, so we don't need to do that. We just take the difference of square of functions and then evaluate the integral. Okay? So this method is called the Walsh method. In the following example, we consider the solid region formed by revolving the region bounded by the graph of the function y equal to x squared plus 1. Another one is y equal to 0, x equal to 0, and x equal to 1 about the y-axis. So let's see, what is y equal to x squared plus 1? So that is the parabola, right here. Okay, so you just have parabola x squared and then you just shift that, right, off on one unit, so you get this. Y equal to 0 is this one, means the x-axis, right? That is y equal to 0. X equal to 0, that is the y-axis, okay? And x equal to 1 is this line. So our planar region looks like this, okay? And now we revolve this region about the y-axis. You get this solid region. And we need to find the volume of this. You see, now we revolve the region about the y-axis. So if you want to use this method, we need to use the formula for the y, right? But again, right, in order to find the formula, in order to apply the formula when you revolve some region about the y-axis, you need to make cuts. Let me erase this. You need to make cuts, right? So the cut would be perpendicular to the axis of rotation. So I might have cut like this. Is that correct? But yes, in this case, when y is bigger than 1, so you have cut like this. But when y is less than 1 and greater than 0, you have cut like this. So basically, you might think, yes, we need to divide our integral into two integrals. The first case, you need to consider the integral from where? From 0 to 1, right? When y runs from 0 to 1. Is that correct? For the second case, when y runs from 1 to 2, so you have difference, the difference is, very big difference in here. Because, the difference in that case is x equal to 1 and this x, this curve. Agree? And this curve, if you express, the parabola, if you express x as a function of y, so you would have the following: x squared equal to 1 minus y, then x equal to square root of 1 minus y. The square root because, you consider the case when x is bigger than 0. Does that make sense? Because usually when you apply, the square root to square, you have plus minus, but x is positive, so you have x equal to just plus square root of 1 minus y. Okay, based on this observation, I may write my volume S. Integral from 0 to 1, let's say pi, from 0 to 1, I have r square is 1. You know that the bigger radius is 1, the smaller radius is just 0. So I have 1 square minus 0 square dy. Is it correct? And when y runs from 1 to 2, I have integral from 1 to 2. The bigger radius, what is the bigger radius? That is right here. It's also 1, right? But the smaller radius is this. So the bigger radius is 1 square minus xy, I write like this, okay? Xy square, and then dy. So I have pi integral from 0 to 1 dy plus pi integral from 1 to 2, 1 minus, we have x over there, that is square root of 1 minus y square, and then dy. Now let's solve these integrals, and we have what we need. The first integral is pretty easy, that is pi times 1, right? The second one, let's see, 1, 2, 1 minus 1 minus y, and then dy. So if you simplify this, you will get just y integral from 1 to 2 dy, right? Let's find this separately, and then that is 1/2 y square from 1 to 2, and I have 1/2 2 square minus 1 square, so I have 3/2. I think I do some mistakes in here when I solve the x with respect to the y. Sorry for this. So you know, let's do that separately in here, otherwise we get wrong in this term. So we have y equal to x squared plus 1. From here I get x squared equal to y minus 1. So I have x equal to square root of y minus 1. So please, let's change this. In here I have y minus 1. In here I have y minus 1. Okay. So we will have this is integral from 1 to 2, 1 minus y plus 1. So 1 is still there. Integral from 1 to 2, 2 minus y dy. Okay, and that is 2y minus y squared over 2. Evaluated from 1 to 2. So you plug 1 and 2 into the function, you get 2 times 2 minus 2 squared over 2 minus 2 times 1 minus 1/2. Okay, you simplify this, you get 4 minus 2 is 2 minus 2 plus 1/2. So basically that is 1/2. Okay, so the integral is 1/2. You plug 1/2 into this, you get pi plus pi/2, because pi times 1/2, right? Which is 3 pi/2. Alright, so that's how the washer method works when we rotate some region about the y-axis. Right? In order to finish this video, let's consider a very interesting problem, and I think that is, you know, you see that almost everywhere, right? So if you have a ring, a metal ring, okay, so like this. So how to make a metal ring? They drill a hole through the center of a metal sphere, right? They start from a metal sphere and then they drill a hole. And suppose that the metal sphere has radius of 5 inches, okay, right here. So you have 5 inches, that is the sphere, and then the hole has the radius of 3 inches, right? So they make a hole right here, okay, and you have a ring, okay. So what is the volume of that ring? Okay, so they ask us to find the volume of the ring. We need to use the wash method. Why? Because, you know, for such problem, of course, we always need to find, always need to draw the plane region. Because the plane region is how we can see, right? How we can see the plane, and then when you rotate, you see what happened. And in this situation, of course, you rotate about the x-axis, right? Because you have, if I just make a copying here, so here's 5, so here's 3, so my plane region look like this. Is that correct? And then you rotate this region about the x-axis, you have the ring, right? So since we rotate about the x-axis, our cut, planar cut, should look like this, which is perpendicular to the axis of revolution, right? So by the Walsh method, the volume looks like, I can write the formula of the volume equal to pi integral from where to where. So we need to find this point and this point, right? But what is that? Actually, you can find that is equal to, so when you cut this from here, this is 5, so your cut is 3, radius is 3. So if you want, you can use Pythagorean theorem, right? You may find the Pythagorean theorem and to find the coordinate of this guy, because in this case, even you have sphere, right? The sphere, so this is the radius of 5, but when you already make a cut, when you drill a hole, so the interval of integration should not be from -5 to 5. It should be from where in here to this guy, right? And we need to find that out. Okay, so let me write that is from somewhere in here to somewhere in here. The first function is Rx square minus R small square, and then dx, where the bigger one should be what? The bigger one should be this, right? Because this is Rx. So that is what? That is the sphere. So the sphere looks like, yeah, of course, that is that is circle, right? Because when you consider planar plane region, so that is a circle. So I can write that is, I write here circle, okay. And the smaller one is 3, The smaller one is 3, because in here this straight line is nothing but y equal to 3. So I have 3 in here. Now our job is to find R capital X, and then to find the integration limits in here. Okay.